This section ties into something that you may have covered back in college algebra or even earlier than that. And that was the idea is if you have a quadratic equation, and I'm writing out all the possible terms here that you could have in a quadratic equation. So this gives us any term that's up to degree 2 involving two variables x and y. And normally when you see these in college algebra, they leave out this xy term here because it's a lot harder to try to graph it and do what's going on with this when you have that. When you get rid of the xy term, then it's either going to be a circle, or it's going to be a parabola, or it's going to be an ellipse, or a hyperbola. These are all the conic sections here. But when you have the xy term there, it's harder to figure out what's going on, where your foci are, and all that stuff. And it turns out, using the techniques of what we learned here, there's an easy way to get rid of the xy term with a change of variables. But it involves a lot of theory getting to this point. So the idea is, whenever you have a quadratic equation like so, whenever you have this type of quadratic equation, we're going to create a matrix, and this matrix is going to have A, B over 2, B over 2, C here. And the reason why it's going to be like that is if you take the following, if you were to do x, y multiplied times this matrix times xy, what you are going to get here is you are going to get ax squared plus bxy plus cy squared. That's the first terms in my quadratic equation, and this is going to be what's called a quadratic form. Basically, this matrix here is going to encode all the information on the degree 2 terms in your problem. And so, okay, what are we going to do with this matrix? It turns out that if you let this be A, and you find the orthogonal diagonalization for A, PDP transpose. Remember the orthogonal diagonalization, the P inverse is the same as the P transpose here. Well, if you do that, and you're going to change your variables here, I'm going to call the new variable x prime, and the new variable x prime is equal to P times x. So what I mean by that is my new variable x prime, y prime is equal to whatever P is times xy. Then if you make this change of variables and you get a new equation that has, x prime squared and y prime squared and so on, it's going to turn out you guarantee that you are no longer going to have this cross term. This will not occur in the new variable version of it. So it turns out that we have a perfectly methodical, repeatable process that will let us get rid of the xy term in any quadratic equation. And once you get rid of it, then you can go ahead and maybe do some completing the square and end up getting the center, the radius, the foci points, whatever it is you're looking for there on your ellipse or circle and whatnot. You can get all that information once you've gotten rid of the xy term. So let's do an example of this here. Let's start with the following. Let's see that 13x squared minus 10xy plus 13y squared minus 72 equal to 0. And so the directions would be the following: perform a rotation of axes to eliminate the xy term. That's what we're trying to do here. And so, okay, so we have our matrix A that we said you put your A here, and your B over 2, and your B over 2, and your C. And if you didn't notice before, this is a symmetric matrix, which symmetric matrix is what we need in order to have an orthogonal diagonalization. We saw that in 7.3. And so we do our whole process here, determinant A minus lambda I. Skipping a little bit of the steps here. 13 minus lambda squared minus 25. And that'll be lambda squared minus 26 lambda plus 144 equal to 0. And this one you can factor lambda minus 8, lambda minus 18. And so we get our two eigenvalues. Lambda is 8 and lambda is 18. And then once we have those, we can go ahead and find the P matrix. And once you have the P matrix, then you're able to do your change of variables, right? So we'd have to figure out our eigenvector for lambda equals 8. So lambda equals 8 would be 5, negative 5, 0, negative 5, 5, 0. You're going to get this here. So you're going to get x is y. So we have 1, 1 here. And then we'd get lambda is 18. And let's see what we're going to get here. We're going to have negative 5, 0, negative 5, 0. And then we're going to have the following. We're going to get 1, 1, 0. So x is negative y. Negative 1, 1. We do have to make them orthogonal, right? So we need to make them unit vectors. So then my P matrix here is going to be 1 over root 2, 1 over root 2, negative 1 over root 2, positive 1 over root 2. And that means my new variables here are going to be x prime equals P times the original variables. And so then you have to solve for what x and y are in terms of x prime and y prime, which is not that hard because it's going to be, orthogonal matrix, so the inverse is the same as the transpose. And in this particular case, the transpose is just going to switch the negative and positive here. And so what we would do then is we would say, okay, that means x is 1 over root 2 x prime plus 1 over root 2 y prime. And y prime is negative 1 over root 2 x prime plus 1 over root 2 y prime. And then we would plug these up here into each x and y. And then when you do that, the x, y term is going to cancel out, which it would be a whole lot of work right now to do that. And so I'm going to let you in on a little secret right now. It turns out that you can skip all of that work, and once you get the eigenvalues, so you can skip all the eigenvector part here completely. Once you get the eigenvalues, the simplified version is going to be just the first eigenvalue, x prime squared, plus the second eigenvalue, y prime squared, and then you keep the constant term there. And you can do a little bit of work here, dividing by 72. You get x prime squared over 3 squared plus y prime squared over 2 squared equals 1. And so that tells us that we have an ellipse here. And the axis on the x-axis is going to go out 3. So this is 0, 1, 2, 3. And over to negative 3. And it's going to go up and down 2 here. All right, so the process, if you want to do all the steps, yeah, you find the eigenvectors, you do a substitution. But because of the fact that we're making orthogonal vectors, they're usually going to have weird square roots in them. And you're squaring things, it's going to be a gigantic mess if you try to actually plug it in. But it turns out the shortcut means you just need the eigenvalues and you are good. And that's all we have to do here. So what I will ask you from this section is I will ask you to take a quadratic form like this and ask you to eliminate the xy term in it. And you're going to do that by just this exact process here. You're going to write out your matrix A. You're going to find the eigenvalues of it. Once you find the eigenvalues of it, you are going to go ahead and write out your new quadratic form like we did down here. And then you're going to go ahead and simplify that in order to get the what shape it is and what your minor and major axes are. So I'll ask you to graph your answer in the new coordinate system like I did on the screen here. So that's the type of question you'd expect on this section. Really, all it comes down to is writing your matrix A and then getting the eigenvalues of it, which shouldn't be that much work for it. It's just there's a lot of cool theory going behind it that explains, this actually working this way. But for us, we're doing more computation in this class, and so just being able to get the answer here is what we're important. Now, I will say that if you were in a situation where your original thing had linear terms like just x and just y, then there is a problem there because that would have to be plugged into your new x prime, y prime. You would have weird square root terms in there. It'd be a real hassle to deal with. Furthermore, it would be harder to find like your center of your ellipse and so on because you have to do completing the square with weird square roots in there. But for what we're going to have on our test, I'll make it so that the x and y terms are not there so that we don't have a problem with it. But this is the extent of what you need to know for 7.4 for us. There are actually quite a few other things in 7.4 that we are not talking about. I was just trying to talk about quickly what quadratic forms are and how you can essentially diagonalize them or get rid of the xy term. In terms of this section, it's called rotating your axes.